Okay, part two, physical and virtual memory. How does virtual memory works? Virtual memory is the idea of creating a logical space for keeping the memory of the data and the code. The backing of logical space with the real and physical memory according to the set dynamically maintained table by the OS. The virtual memory is limited um, only by the theoretical address possible accessed by the computer architecture. In Win32-bit environment, a user process basically uh, require 4 gig. Uh, 2 gig is used by the kernel, 2 gigs is used by the um, each of the process. So we need to separate these limited physical memory, mainly is what we call the RAM, uh, is to be used by each individual running process inside the operating system. So the OS need to set up for each of the process a table to maintain the table of the virtual memory so that multiple virtual memory user process can share the use of the physical RAM more efficiently and securely. So that is a couple of objective or reason we need to maintain. Each process needs to see a dedicated logical space of memory. The physical space must be shared out sometimes, especially those system DLL. It may be shared in a very messy way. However, the physical memory is not seen, is not accessed directly by each process. Each process can access its only virtual memory space, and that kind of work is handled by the Windows kernel part. Processes cannot interfere each other so that they are more securely protected without interference by the other process, unless somehow the mapping table have been met with the same physical memory in both process virtual memory address, that part what we call the share memory. Um, we need to have some memory layout to handle the efficiency of use of physical RAM or physical memory because each process may have a big gap, especially in the part of heap or the stack when they are not using. The OS will not map that part of memory from the virtual memory to the physical memory unless when that particular process is handling by the processor and the processor need to access that part of the virtual memory, and then the OS will step in to do the mapping of the accessing gap of the memory in virtual space to the physical memory. That part is what we call the demand paging. The physical the problem and the data, sometimes they need to be shared as I talked before, so that it will be more efficient for those frequently use the data or code be kept inside the physical RAM, mainly the in the RAM part, and then that part will be marked as shareable. So each process can share this part. Sometimes they are read only to uh, save the time for loading the image from the hard drive to the memory to be used. Somehow we need to have ask the OS to take part to create some kind of memory hierarchy. So the physical memory can be mainly using the RAM part, and then the other part when if in the situation the physical RAM have the RAM part have been fully or almost fully used, the OS will find some part of the memory in the RAM they are not, even though they are mapped, but they are not using frequently, they will be written onto a file called swap file. That is how the OS handling the activity right there, like this. Okay, right now we shall go over a few slides talking about the overall concept of what we have discussed in the previous slide. Here we have some diagram on the left side, hand side. We make some assumption. The program address is exactly equal to the RAM address. Here on the blue column is referring to a 4 gig user process, assuming we only have one user process. The mapping is, if the situation, if we only have a 32-bit RAM, which is equal to 1 gig address space, if we do the one-to-one mapping and some of the program address space will not be able to map. In this case, the OS step in, the OS try to create a map. Then each byte of data or each chunk of data will be mapped, handled by the table created by the kernel, and then some other pointer in the memory to the physical RAM. So that is the way to prevent any virtual memory program will accessing by the two process together to prevent any data crash. And that is more flexible for us to handle multiple memory process of the virtual memory request, but we only have limited physical RAM. Then we talk about the memory isolation. For example, right now, if we have two processes, here is we specially create two processes with different process memory, logical memory requirement. Each process may, for example, in program one, need to access the address with the OX, the hexadecimal address of 1024. And another program also, if they are mapping into the address 1024, in the previous example, there will be a crash. But right now, if we create not only one map, but we create two maps, each map is mapping to each program, then the OS can handle the mapping from the address 1024. When they are accessing the physical RAM, they put in the number 2 RAM location for the program 2 with the same logical address of 1024 will be mapped to the address number 5. So there will be no crash, and that kind of activity is handled by the OS. This is another layout that the physical memory, for example, the program number 3 and program number 2, both of them, they do have the mapping. So if the memory is handled in form of a fixed size so that they can fill in the physical RAM, just like a drawer, a cupboard drawer, you can put the data inside the drawer in a fixed size. It's more easier to handle. So when any part of the large gap of unused memory, they will not be wasting to be idled. So by that kind of way to handle a fixed size of data, usually these fixed size of data we call the page. So if we are measuring, for example, this part of data, we have a kind of the Windows kernel will making use of some kind of mechanism to handle the data. They first are referring this chunk of data, for example, this second block, they will not name it as second block simply. They referring to two pieces of information. One is the base pointer of a particular chunk of data, and then the offset at the offset, base plus offset. If you're referring to back to our PE lecture, talking about PE image, also we talk about the virtual memory. We measure by the LVA. The base is the image base. For example, if the bintext binary, they are having the entry point LVA is 442D, but with the bintext, the base address at the address logical or virtual or process address starting at the base of 400000, then add up the base plus the offset, that the virtual memory's entry point should be at 40442D. So the same logic when the OS handling the memory mapping from the virtual memory to the physical RAM by calculating the base and the boundary. So sometimes each of these base is handled by the base data contained in the part of the register. And also from each boundary, we may have different boundary location. For example, this is one boundary, this is another boundary, and this boundary is contained in the base address on the segment register. So this is the another case that if a physical area they contain some shared region, and this region sometimes a lot of program may be required to access or modify the particular commonly using data area for if this part is containing the system DLL frequently used by most of the process, then this part will be marked by the OS as share, so that we don't need to load it or unload it or write it into the swap file so frequently to maintain the efficiency of the using of the physical RAM. And this part is what we call usually they are not private. That is, the share means it is public, right? For any particular location have been mapped and used by the particular process. In this example, this address space is called private working space. If a chunk of data right here, we call the private use of the private use working set. Okay, so they have different terminology when we are using this part of data. So share only allow the no private working set. Here we have a more complicated situation. The virtual memory of the operating system applies a method called paging. As I said, a fixed chunk of the data to map to from the virtual machine, virtual address space to the physical address space in such way that all processes can get to run on the physical memory if they are required. If physical memory is insufficiently large to accommodate all the process, then the one-to-one mapping cannot be happen. Then some part of the virtual memories will be handled by way of a table, and that table, whenever the table reserved by the used by the OS, then that part we call the committed virtual address space. And whenever committed, that means that the OS need to be paired. Well, I need to reserve a special port of the RAM because that particular part of the RAM has been reserved, has been committed to allow the process to use to be accessed. So if the physical memory is less than the combined memory demand or commit for all processes, the virtual memory manager residing in the Windows kernel will have to load each process sequentially in the physical memory and wait until the process ends. And when the process ends, it will release back that physical memory to allow other processes to use. So that is the way the kernel part of the Windows that part is called the virtual memory manager of the OS to handle. The virtual memory manager, we call the VMM, allocate the consecutive address in the virtual memory in unit. And that part of unit, fixed unit, is called page, as I said before. And they maintain a page table just like this. Whenever they find a virtual address like this, and then they do the commit the address of the physical address of 12 in this table. So the table, other than the pointer address, they also contain some kind of metadata. Whenever is the physical address has been used up or almost used up, and the OS may mark this, okay, this is, I need to save it into the hard drive in form of swap file. So these of this kind of arrangement is called the paging from the physical RAM to the hard drive. If we can always be found in the physical RAM, we call the non-page one. Okay, so why we are using the page? Because each time when we write data onto from the physical to do the translation, we reserve that part of the physical RAM in form of fixed size. Each size it consists of a certain fixed amount of address to be reserved, and that part of size in a typical Win32-bit environment is 4K, that is 4096. If that part have been assigned to hard drive, the hard drive will write in a basic chunk size of 4K. So this is what we call the paging and the release and the reserve or commit, if part of the data page have been publicly accessible, that is called non-private working set. For this example, if they are originally this page R5 has been saved in the physical RAM, but suddenly this part is we find they are not frequently used. The OS will the VM memory will allocate. We want to release this fast RAM to the other process use and then write this information to the hard drive. And after a while, if the OS find that this part need to be used, they part of the data will be upload back to the physical RAM to handle. So this is kind of arrangement we call the demand paging. Okay, we come to a very, very complicated diagram. At this moment, you don't need to too much worry because I already create this slide so that you can interactively see how the relationship or more complicated Windows OS, VMM, managing these multiple table. So these multiple table actually used managed by the OS plus part of the management or administration handled by the processor that is inside the CPU to do the memory mapping. To simplify the arrangement, basically, we go over the step like that when with the help of the OS, all process access the coil, the code data and data or data to the virtual memory, but not the physical memory, just like the model that I showed, simple model that I showed you in the previous slides. And then the memory manager, we call it a VMM, uh, that is handled by the OS, keep a page table for each process. And allow another part is called the MMU, the Memory Management Unit. That is the MMU is the hardware circuit handled by is contained inside the processor. Uh, Both of them work together to handle the uh, memory mapping in an efficient way. There is another hardware circuit is called TLB, called the translation lock aside buffer that is contained inside the processor, which is a cache to maintain on the MMU, the memory management unit, to store the page table uh, to help the CPU and the MMU to run faster, fast allocation of the virtual memory to the physical memory. So memory controller is the hardware circuit responsible to control all possible connection, concurrent requests, and blah, 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 together working with the OS to make these virtual memory mapping to physical memory and to keep the security as well. So basically, it comes from the one of the register called CL3 inside the processor. And from the CL right here, the CL goes to a table, the base physical, just pointing to the base. And then from the other table, it will find out some page directory entry, and both them create a pointer from the pointer point to the base of the page table, and the page table based on another 10 bit of data inside one of the linear address. It will go to the page entry, and by adding the another 12 bit of data. Why 12 bit later I will explain to you that is exactly why I said 4K data, because 12 bit is by the power of 2 is representing 4096 unit, and then that point to the physical memory. That is the way to how the physical memory map to each process. In memory forensic, we do things in reverse, because when we acquire the memory dump, we acquire the physical memory. At the back of the there is some kind of algorithm and logic. The volatility, the tool that we are using is take out these table and the content of the CL3 register reside in particular shared location inside the physical memory. And then based on that part, it can reverse calculating by the physical address offset to find out a particular location of the ePROSESS structure or any kernel object structure, so that we can have more contextual analysis of the memory information of a particular kernel object. Based on that kind of thing, we can have a wonderful and contextual analysis of this physical memory. Here, I would like to jump on one part to remind you first. Inside one of the register called GDTR register that contains 48-bit of data, and part of them is the metadata, which is control the accessibility of the physical RAM in between of user process or the kernel process. If that is in the kernel process, that and everyone should remember that I said any that is a formal in the controlled by the CPU register information, and that is 2-bit, so that we have formal from the basic mode is called we call the range 0, another is range 3, and Windows system only using 2 bits to handle the privilege or the user or super user um, permission. So that is also contained inside this page directory entry. Okay, so we now go to the free model. We go over this model one by one. Okay, physical model. Here I present you with some interactive slide. The physical model, we assume a physical address that is the accessible by the processor and make some comparison. Okay, here I assume each page is 4K in size, and that is the physical memory. And here the participation of the 32-bit CPU. Before we go into the detail of the 32-bit CPU, we need to go to another physical model in the old days. Sometimes some of you are too early for you because you are so young. We talk about processor of the X084, the first Intel processor available for the we call at that time called the personal computers, and used by the IBM, so that at that time they call the IBM compatible processor. So at that time, that CPU size is not 32-bit, that is 20-bit only. And 20-bit by the power of 220 of the to the power of 2, sorry, the 2 power of to the power of 20, the maximum memory accessible by this 32-bit CPU is 1 meg. So that is highest capable amount that a 8088 processor can access at the same time. So when we go to the 32-bit CPU, the size will be dramatically changed because there is more 12-bit available accessing at the same time by the CPU circuit. So the maximum accessible physical memory will be 4 gig. That so similar to a 32-bit Windows system, 4 gig. If a computer only allowed to one process, so we can do the one-to-one mapping by using the physical memory. So now we go to the fat memory model. The fat memory model, unlike the physical model, the linear fat memory model memory somehow is some kind of abstraction. Under the flat or linear model, memory appears as a continuous sequence of bytes that are addressed starting from 0, or what we call the offset 0, and the ending at any arbitrary value arbitrary offset that marked as n, whatever. In that case, n is a typical equal to 2 to the power 32 minus 1. So we have a bilinear address mapping to the physical. Both of them are 4K in size here, and typically in example in the practical use is 4K. And how this linear address be assessed, they come with two parts. One part is the one data chunk in the blue color, and this blue color, and this blue color can map to here or map to here. And this yellow color can map to here and also can map into any chunk of data. So this is what we call the mapping. And calculate when we are assessing the memory segment, we are referring to other table. One table is what we call the segment table, and this table may be handled by the segment register, and the segment register only pointing to this chunk of data, the base of this yellow kind of data, and the offset that shows the from the base plus the offset to find the exact location in the memory segment. So that part can map to the linear address. Linear address can map to the physical address, something like that. And the offset basically is calculated by two pieces of information in a table that is called segment selector plus the effective address. So that is the way how the multiple table of virtual memory map to the physical memory. So if we need to do this as an example, we have the segment selector pointing to the blue base of the blue segment, and the effective address, that means the offset, and then this offset map to the linear address, and linear address can map to the physical address. So we are assuming the linear address is exactly equal to the physical address so that we can do the page by page mapping. But what if the linear address, we don't know the size, or the size much less than the physical address? So we need to have some mechanism to handle this kind of thing. So each part of the data, we need to have more efficient use of the memory, physical memory address. We are keeping this fixed size of n byte to a fixed unit. If we handle it as a page, it won't be any inefficient use of the empty space. Now we come to the segmented memory model. So segment model, we still have two modes. One is what we call the view mode. Unlike the FAT model, the segment memory model is somehow some kind of abstraction. Under the segment model, memory is viewed in terms of the distinct region called the segment. And the byte of an address in a particular segment is designated in terms of a logical address, like the FAT model before. A logical address is known as some kind of pointer and offset plus the segment base. The segment base is residing in a CPU register. We call it segment selector or segment register, just like this blue one, and which is determine the final destination address of the linear address and imply to the physical address. This is a 20-bit CPU environment. It only have one map in size, and in this real mode 20-bit CPU, basically the effective address is 16-bit and the segment address is 16-bit, can come up with the definite location. So we need to add them they have some kind of implication zero add together to find the exact location of the physical address. That is the way of the linear address map to the physical address. Now we are going to the protected mode of segmentation model. Unlike the real mode, the protection mode is the instant of the segment memory model. The differences is this process of physical address resolution is not confined to by the processor. The OS participant must collaborate with the processor to maintain overview of the special table that will help the processor to finish the mapping job, while the extra bookkeeping put additional burden on the operating system. However, the segment selector is 16-bit in size and effective address right now is 32-bit. And the segment selector is not referencing the linear address directly, but they have a way to put another table here. We call the GDT table, which keep the segment global description table. And the one of the register called the GDTR register, that register can access 48-bit of data, and this data is kept on form of a table called segment called GDT table. Based on that, we do more additional handling because the GDTR register is 48-bit. So 16-bit is determined the GDTs, which is equal to 8,192 byte. Why 8192? Because 16-bit, it comes to that kind of power to the 2. You can calculate the number, the maximum accessible size. The remaining 32-bit store in the base to base effective linear address of the GDT table. So if we are using WinDebugger, we can using WinDebugger to read these IDTR and GDTR register data inside the kernel. Even though we referring that kind of information is called the register, basically that is the current value of the register inside a particular process. So that is kept also inside of the kernel memory. So here we come to the protected modes arrangement. Inside the GDTR register, it have a pointer to the GDT table, the base of the GDT table. In order to find the GDT table more accurately in the, we need to have another piece of information we call the offset. The offset comes from another 16-bit offset. It's coming from the segment selector. And inside the segment selector, that is 16-bit, in this segment selector, which is the metadata and the pointer of a particular effective address, 32-bit is indexed to the reference of GDT entry. However, bit 0 and bit 1 is handled, is used to define these memory address is protected or privileged or the non-privileged mode. And this is what we call these 2-bit to define the range 0 and range 1, range 2, and range 3. So this is called protection bit. And then the 32-bit effective address is kept inside also in another part of the segment descriptor table called the effective address. If we add the effective address plus the content of a particular location of the segment descriptor table, we can have they are assessing which segment. So for example, this is blue one, it pointing the base address in the get the base address from the GTT table. And then the effective address 32-bit is referring to the offset from this location. And then it can map directly to the physical address. And the physical address contained inside the physical RAM. Now we come to another concept we call the segmented model with protected mode with paging. So it's more complicated right now to save this unused space. Multiple level of page tables are used. The MMU, the CPU, we have the MMU here, TLB here. The TLB is the buffer, MMU, the management unit. The MMU is the hardware component on the CPU, which handle the mapping piece of the virtual address to the equal size of the space they place in the physical memory. That equal size we call the page. In this way, when CPU goes to read from or return to or write to a memory location, it indicates the location in the virtual memory numbering. We call the virtual address. The MMU does not keep. The MMU does not keep the keep track of the association between the virtual and physical memory on a byte-to-byte basis. It works in terms of the unit called page and page frame. Right here, the base is the, this part is called whole page, this part is called the page frame. Virtual memory is divided into the page according to this kind of arrangement, just like the physical memory, so that the moving of data is more easier, and there's not wasting of unused memory gap inside a virtual or linear address. The performance of the page table is improved a lot when the TLB step in. TLB is the translation look aside buffer, which is a cache in the register more far that is circuit inside the hardware of the CPU, so it can handle the mapping of the page to the physical from the logical memory to the physical memory more faster. If we find the linear address, we can take out with this 32-bit address into three parts. One part is what we call the directory 10-bit. Another part is the table bit, also 10-bit. The remaining 12-bit is the offset bit. So actually, there's a register, as I said in the beginning of this section, that is a register called CR3, which is 32-bit pointing to a base of the page directory. And the first 10-bit is measured containing the offset from the base address to the location of the directory. And the directory contains another piece of information. This information is called page frame number, PFN. And you see that 10-bit means 1024. It comes from the 2 to the power of 10. So maximum value, maximum entry in the directory table is 1024. The same logic, this address is pointing to the base of another table. That table is the page table, PTE. And the PTE do have an offset kept by the linear address, the middle 10-bit of the linear address. And because that is 10-bit to the power of 10, it comes to the 1024. And the remaining part, 12-bit, is 2 to the power 12, which is exactly equal to the 4K, which is 4096. This is the reason why we always say that in Windows 32-bit environment, they are each page size is 4K because they are limited by the linear address, the offset 12-bit inside each linear address. And the address is come from GDTR, come from the segment selector, come from the effective address to do the calculation. And by combining the page table entry content plus these 12-bit data, we can directly map to the physical address. That is the way how the CPU working with the OS to keep multiple tables to find out the final address of the physical memory. Hope you can understand by moving this relationship. And we don't need to remember the whole details a lot because when we performing the, we just need to understand the fundamental logic. And that is the way actually the volatility tool, once they have the physical RAM, by checking this table, they can calculate back to exactly what is the relationship from mapping from the logical memory of a process to a physical address. Here is an example. I always like to using one of the standardized binary in the our virtual machine called BeanText. We load BeanText with the, we execute the BeanText, which is inside running process, that is logical process. And then we can call up another sysinternal tool called the VMMap. By using VMMap, we can see, for example, here we can see the term called committed. That means that OS committed and mapped these virtual address to the physical address. And you will see that the committed of the physical memory to this BeanText process only limited to 68K byte. Is not large. And part of them in the purple color that is only used by the image. That is the image of the BeanText is only using only half, almost half of the 68 byte. And some part, for example, in the orange or the brown one, you will see that as the heap. Except when we click into different section of these part of information, you will find the content and show that some of them you see the share was when we find the share, that is some kind of marking in the table, part of the table to show that that is shared part. Some of them are unusable, and the free, total free, for example, that is 2 gig, 199 something, and that is accessible, logical, or virtual address by each process. So this is a nice table mapping. You can check the details, and actually, when you find the BeanText, for example, it mapped into the virtual address, and the virtual address, the base address is start from 40000, which is contained, this value is contained inside the PE file, a particular PE header field. And each of them may contain different sections. For example, the hex section marked here is called executable and readable. These marking, when we referring back to the PE internal or PE lecture, I told you it is defined by a 2 byte, we call the characteristic byte of each segment inside the PD segment directory, and that is the marking to determine when Windows loader load this information already marked based on these 2 bytes as executable and readable. And also some of them read, some of them read and write, depends on how the table be configured. Here, I would like to show you more about the virtual memory of another famous I always like to use a process called Notepad. I open Notepad inside the Win32-bit environment. I also open the Notepad in the 64-bit virtual machine. In the 32-bit environment, you will see some interesting thing. For example, we have the working set. You can find the information of the working set. And also some of them are called private working set, which is already committed by the OS to this Notepad process. And the working set of a process basically comes with 2 parts. One is shareable, which is public working set. Another part is private working set. And commit means the amount of virtual memory reserved by the operating system for a particular process. In this example is the Notepad. Okay, so the amount is only some kind of estimated amount of the page file size needed, and actually that committed doesn't mean it always all allocated, but is allocatable. So in the concept of the virtual memory, we can be able to find the total virtual memory right here is some kind of representation of physical memory plus the page file in the swap file. And interesting thing when compared with 32-bit, you will see that the size, even though the binary is the same binary, but one of them compiled by Win60-bit environment, whereas in 32-bit environment, the size almost not a significant change. But here, they are similar, but the working set is represent, as I said, working set means the private working set plus the shareable working set, much more higher, larger in the 64-bit environment. But the most important part is the free remaining unused, uncommitted virtual memory size of the 32-bit environment is almost equal to 1.9 gig. But you will see that in 64, that is a very big figure right here. Okay, so, and you see also in 32-bit environment, we are so familiar with the heap and size and the magic number, or I call 7 or less. Any size will start with the 7 or less in user mode accessible. And the VM map is a user mode process. It cannot see anything below inside high with the kernel memory, even though they are virtual. The VM map cannot see it, so it will be limited with the 7 something. You cannot see the 8 number higher unless you are in the local kernel debugging. But in 64-bit, you see the size is more complicated, more longer, but they are more or less the same. Okay, so that is the reason why I want to show these pictures right here. And you can play around the VM app, and whenever you come across with the concept of sometimes terminology, committed or reallocated, virtual memory, physical memory, working set, private working set, and shareable working set, all of them are covered in the previous discussion